Good day, ladies and gentlemen. Lab 3, intermolecular forces. The first thing that we'll profile or try and understand is why certain things dissolve in each other. So if you read the lab, you will of course know about the classification of intermolecular forces, dispersion forces between nonpolar compounds, dipolar forces between polar molecules, special case of hydrogen bonding, ionic and whatever. And so, as we've described in the manual, and thanks for reading, digesting, understanding. You don't read it as a novel, you read it slowly, repetitively. That's how everybody gets it. So, the central idea is that you must have favorable solute-solvent interactions for a solution to form. So, in the pre-lab, you profiled or described the dominant intermolecular forces in the solute and solvents, and so now we will actually profile them to see what happens. So the first one is pentane is the solute, cyclohexane is the solvent. So I have cyclohexane in here, and I'll get some pentane, a little bit, or a lot in this case. By the way, I don't know if you noticed, it was just dripping out of the thing here. There's a good reason for that we'll understand later. So I've gotten the two. In the case where we are looking at liquid to liquid, then if they don't dissolve because they have different densities, they'll actually come out as different layers. And so in this case, I don't see any layers, do you? So this one kind of mixed nicely. Pentane and cyclohexane. All right, moving to the next one. It says sodium chloride, table salt in cyclohexane. Interesting. Sodium chloride is a solid, of course, as we all know. Let's get a little bit, not a whole lot. Of course, we know you can add enough sugar for the thing to be insoluble. How about that much? All right, let's add it in. It might look clear here, but if you look in the bottom, it's all sitting down there. It's all sitting at the bottom as a white stuff at the bottom. So that's our result then in the case of sodium chloride and cyclohexane.
Close look.
Look
Against
for
the
close.
black background.
Moving along, my friends, acetic acid, pure acetic acid, people refer to it as glacial acetic acid. Smells like vinegar. Well, the active ingredient in vinegar is acetic acid, as you very well know. We take some here. You'll notice acetic acid is not dripping, except I'm pressing it. 5 or 6 drops, even more. That's a little storage thing there. Shake it. Shake it. Look in the bottom, nothing. Look for layering, nothing. So, again, just to be sure, acetic acid and cyclohexane. All right, moving right along. Next one. Sodium stearate. Sodium. So it's an acid group in the long chain of carbons. You can look up the formula. So it's essentially an ionic compound. Yeah, it's one that you gotta think about the kind of intermolecular forces that are operating in it. A little bit. Come on, it's so powdery. That much sodium stearate. Down. What are going to give us sodium stearate? And it says, it's a little cloudy, whatever it is, but I don't see any stuff sitting in the bottom or floating around. So, looks like the sodium stearate completely dissolved in cyclohexane. If I close up. All right. The sodium stearate out of the way. Next one is the acetic acid out of the way. It says water in cyclohexane. And grab some water on the other side here without spilling anything. So water in cyclohexane. Use the wash bottle, that should work. I'll put some more, there's a good reason why. In this case. Shake it. Right, so in my last test, kind of messed up a little. Oh Lord. I thought I had cyclohexane in the bottom and then I was adding water. But actually we have water down here. Go figure. Pray for me. We have water down here. So water down here, that's the solvent, and we are adding various things. Beginning with the same, pentane in this case doesn't matter. Again, dripping. Encourage formation of solution by shaking, and in this case, just as you might expect, you get a layering of two different layers. We know oil floats on water, right? Yeah, even I know that. Yeah. All right, moving along. Can you explain that? Yes, you can. Intermolecular forces. What are the intermolecular forces in the solute? What are the intermolecular forces in the solvent? How do they match up? And do they favor each other? Sodium chloride in water. Ooh. What is the solvent? Sodium chloride. Should I even do that? Come on, man. Yeah. Okay. Yes, I will. Salt in, a little salt in water. Sodium chloride in water. Make sure I'm doing the right thing here. Of course, we know what the result is here. Complete solubility. We look underneath there. There's nothing sitting in the bottom. Hey, but we knew what would happen in this case anyway. Right, moving along. Sodium stearate. Sodium stearate in water. Where is my good friend sodium stearate? There you are. Sodium stearate. Stearate. How would I know? Look up the formula. Very powdery and sticky. Right. Put it in there. Did anybody notice anything? It's lathering. Hey, like kind of soap. You put soap in water and you shake it a little and you know what happens, right? Yeah, but generally, lathering, yes, but certainly a nice solution form. Sodium stearate in water. Of course, if I let it sit, the lathering will go away, but you know that. All right, sodium stearate in water. There we go. Right, moving along. Life is good. Chemistry is good. If you were here, you'd be talking with your friends, interacting with your friends, talking and figuring out what's the correct description of things. That collective learning, that partnership, that group work is very important for learning. But hey, pandemonic days, and so here we are, doing things a little different. But we'll get there. Stearic acid in water. What's the difference? Sodium stearate, stearic acid. Look it up in the formula. One of them is molecular with an acid group. And the other one is ionic. Man, picking up a big chunk. I don't want that. Come on, man. Either too much or too little. There we go. Stearic acid. What do you do when we put you in water? Because, come on, man. Interesting. It's actually less dense than water. Particles float. So here's a challenge. The challenge is to describe whether it all got in. Certainly it didn't all get in because some of it is sitting at the top. So do we have solubility? Yeah. Do we have partial solubility or total insolubility? Kind of looking at the amounts there, I'm inclined to think most of what we put in is just sitting at the top. All right. We're done with solubility things. Moving on to the next section, my friends. Now we're going to measure the heights, capillary tubes. These are full of water, soap solution, and the pentanol. I'll start with the pentanol. Kind of tricky here. I don't want to press on top here because that'll push up. I'm going to read that as 4 millimeters. If you can't see, I apologize for that. It's a little tube, capillary tube, and so maybe hard to see. How about we call that 4 millimeters? That's the capillary rise in the pentanol. Moving on to the soap. Soap, where are you? My goodness. You're way down there. Barely up there. I'm I'm going to call this 2 millimeters. If I press there, mess it up. Let's call this 2 millimeters, my friends. 2 millimeters. And then last but not least, good old H2O. Just touch there. I'm going to call that what? 5 millimeters? Let's call that 5 millimeters. All right, and so here is a simple one. The penny. Looking for clean pennies. I had to find around here. So, droplet shape. We know ordinarily around. Why is that? Certainly for water. It's because you're very favorable inside intermolecular attractions. The surface ones are only interacting hemispherically, and so you want to minimize the surface of the area on the outside, and so droplets around. So let's try this. Good old H2O. Count the number of drops it takes. I've never done this before, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. 19. Do I have overflow?
No.
I think so. 19, 20. Now I do have overflow.
Not yet.
You could see the nice shape around. How about a soap solution? Let's try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Overflow. Can you explain that? Why a little soap? There isn't a whole lot of stuff added to this soap. But certainly the behaviors here are considerably different. Considering intermolecular forces. Explain that. Ladies and gentlemen, that's our lab 3. See you in lab 4.